Bismillahirrahmanirrahim. Assalamualaikum, brothers and sisters. Today's episode is a revised version of a past upload on the laws of conservation of linear momentum and conservation of mechanical energy as applied to collisions and projectile motion. So stick around till the end of this video, watch and learn. Problem is a 0.500 kilogram block of cheese sliding on a frictionless tabletop collides with and sticks to a 0.200 kilogram apple. Before the collision, the cheese was moving at 1.40 meters per second and the apple was at rest. The cheese and apple then slide together off the edge of the table and fall to the floor 0.600 meters below. Question letter A. Find the speed of the cheese and the apple just after the collision. In this collision, what is conserved? Momentum, total mechanical energy, both or neither? Question letter B. What is the speed of the cheese and apple just before they hit the floor? During the fall from the tabletop to the floor, what is conserved? Momentum, total mechanical energy, both or neither? We are given the following data and information. The block of cheese has mass M1 equal to 0.500 kilogram and an initial speed V1 equal to 1.40 meters per second, while the apple has a mass M2 equal to 0.200 kilogram and its speed V2 equals 0. So both the block of cheese and the apple are on top of a tabletop that is assumed to be frictionless. So in this problem, our target variables in part A is the speed B prime just after the collision. And in part B, the final speed of uh, the block of cheese and the apple moving as a system, the final speed just before reaching the floor, denoted by B sub F. So treating the block of cheese and the apple as one body system, we first determine the total momentum before they collide. It's understood that the apple has zero momentum before the collision. So we only need the momentum of the block of cheese before the collision. So that constitutes the total momentum of the system before the collision. We compute that by just multiplying the mass of the block of cheese, 0.500 kilogram, and then multiply it by its uh, initial speed, V1, equal to 1.40 meters per second. So multiplying these quantities, we get the magnitude of the total momentum of the system before the collision, equal to 0.700 kilogram meters per second, expressed in three significant figures. To determine the speed of the system just after the collision, denoted by B prime, Uh, we already apply here the law of conservation of linear momentum, which states that uh, the total momentum of the system before and after collisions must be equal. All right? So B prime is equal to the total momentum, okay, after the collision, which is equal to the total momentum before the collision, which is 0.700 kilogram meter per second, and we divide that by their combined mass, m1 plus m2, or 0.500 kilogram plus 0.200 kilogram, which is 0.700 kilogram. So when we do our math, we find uh, the value of their combined speed b prime just after the collision equal to 1.00 meters per second, also expressed in three significant figures. Just to show that in an inelastic collision, such as what we have here in this problem, uh, the total momentum of the system just after the collision is indeed equal to the total momentum before the collision. So we have here the computations for this total momentum after or just after the collision. That is, uh, PT prime is equal to 0.700 kilogram. But that is the combined mass of the cheese and the apple multiplied by their common speed computed earlier, 1.00 meters per second. So we get the amount of or magnitude of the total momentum just after the collision equal to 0.700 kilogram meter per second. Indeed, okay, the total momentum of the system before and after collisions are equal. So we say that momentum is conserved even in an inelastic collision, such as what we have here in this problem. All right, so we have just seen that in an inelastic collision, the total momentum of the system remains constant or conserved. How about its total mechanical energy? Is it also conserved or not? Right. So we calculate for the total mechanical energy uh, of the system before and after collision, starting with uh, the total mechanical energy before the two bodies collide. That is, starting with their total kinetic energy, capital K sub T, that is equal to one half the product of the mass of the block of cheese, 0.500 kilogram, multiplied by the square of its initial speed B1, 1.40 meter per second. So when you do our math, we get the amount of kinetic energy of the block of cheese just before they collide, equal to 0.490 joules. This is already the total amount of kinetic energy of the system, because the kinetic energy of the apple initially or before the collision is understood to be equal to zero, since it is at rest. Now, the gravitational potential energy of the system can be described to be zero relative to the tabletop. All right? So we are choosing the tabletop as a reference in describing or determining the gravitational potential energy of the two bodies relative to the tabletop. Right? It's understood that the block of cheese and the apple have no what we call height relative to the top of the table. So it follows that the total mechanical energy of the system before the collision is equal to 0.490 joules, okay, equal to the total kinetic energy before the collision. After or just after the collision, we also calculate for the total mechanical energy of the system, starting with the total kinetic energy K prime sub T. So that is just equal to one half the product of their combined mass, 0.700 kilogram, multiplied with the square of their uh, common speed just after the collision, 1.00 meter per second. So again, when we do our math, we get the amount of the total kinetic energy just after the collision equal to 0.350 joules, also in three significant figures. The gravitational potential energy relative to the tabletop is still equal to zero because the two bodies haven't changed their vertical position. They're still on top of the table. And so it follows that the total mechanical energy of the system just after the collision is also equal to 0.350 joules. And if we compare that with the total mechanical energy of the system before the collision equal to 0.490 joules, it's obvious that the system has lost some amount of their mechanical energy after they collide. Therefore, our conclusion is that in an inelastic collision, right, uh, the mechanical energy of the system is not conserved. It is because their total kinetic energy is decreased. All right. And the explanation for that is that this kinetic energy, the system, has been converted to other forms of energy, such as heat and sound energy. Moving on now to part B, finding the final speed of the system just before they hit the floor. We denote that as BF. And in the drawing, it is represented, right, by this diagonal arrow. Okay. Now, um, just after the collision, okay, we have seen that the system has acquired a horizontal speed, which we now label as B prime x equal to 1.00 meters per second. So as far as the projectile motion of the system is concerned, right, the system has an initial velocity equal to b prime x of 1.00 meters per second to the right, but it has no downward vertical component. That means by initial is equal to zero. And Before we can determine the final speed of the system Bf, we first have to compute the y component of that Bf using the kinematics equation for freely falling bodies. Bfy equals square root of 2gh, where h here is the height, all right? The height h, meaning the distance of the tabletop to the floor, all right? So substituting, Bfy equals square root of 2 times 9.80 meters per second squared multiplied by 0.600 meters. That is the value of h. So when you do our math, we get the magnitude of Bfy equal to 3.43 meters per second, expressed also in three significant figures. So we will now apply the Pythagorean formula to compute for the actual speed of the system before hitting the floor. All right? Bf is just equal to the vector sum of B prime x, the x component of Bf, and Bfy, the y component of Bf. That is, Bf equals square root of the square of 1.00 meter per second and 3.43 meters per second. Again, when you do our math, we find the magnitude of Bf equal to 3.58 meters per second, also rounded to three significant figures, which is our answer to question letter B. In the drawing, that brown arrow represents the final speed of the system just before they hit the floor. As a follow-up answer to question letter B, uh, we'll show that in the projectile motion of the system, the total momentum, okay, is in fact not conserved, okay, because as we now explain, starting with computing the final momentum when they are still at the top of the table, both the block of cheese and the apple, right? So that is simply multiplying the combined mass m1 plus m2 and their horizontal velocity b prime x, that is 0.700 kilogram times 1.00 meter per second. So that gives us the magnitude of their initial total momentum when they are still at the tabletop about to fall. Okay, 0.700 kilogram meter per second. When the system reaches the floor, or just before reaching the floor, we also compute the total momentum, P sub F, equal to the combined mass 0.700 kilogram multiplied by their final uh, y component of the speed 3.43 meters per second, which gives us 0.240 kilogram meter per second. So this is just the y component of their final momentum before touching the floor. All right? We also determine the x component, P sub fx, that is 0.700 kilogram times the value of b prime x, 1.00 meter per second, which gives us the amount of the x component of the final momentum, 0.700 kilogram meter per second. To determine the final momentum of the system just before reaching the floor, we need to apply the Pythagorean formula. Since momentum is a vector quantity, we have to get the vector sum of the x and the y components. So the magnitude of the final momentum, p sub f, equals the square root of the sum of the squares of the y and the x components, 2.40 kilogram meter per second for the y component and 0.700 kilogram meter per second for the x component. So this will result to a final momentum p sub f equal to 3.43 kilogram meter per second, also rounded to three significant figures. And when we compare this to the initial total momentum at the start of the projectile motion equal to 0.700 kilogram meter per second, it's obvious that the final momentum just before reaching the floor is much greater in magnitude, which leads us to our conclusion that in falling from the tabletop to the floor, momentum is not conserved. And in this case, okay, the momentum in fact increases as the system falls from the top of the table to the floor. And this is simply because the vertical component of the velocity is also increasing, even if the x component is constant, but the magnitude of the downward velocity is increasing. So it follows that the magnitude of its momentum must also be increasing. Still on the projectile motion of the system is the total mechanical energy of the system conserved when it falls from the tabletop to the floor. Let's find out. So we calculate the initial kinetic energy, okay, when they start at the top of the table. So K naught is equal to 1/2 the combined mass, 0.700 kilogram, multiplied by the square of their speed, 1.00 meters per second. And that will give us the amount of the total kinetic energy at the start of the fall. Okay, K naught equals 0.350 joules, also in three significant figures. The gravitational potential energy of the system can be computed, but this time we use the floor as our reference. So relative to the floor, we find the total potential gravitational potential energy equal to the combined mass 0.700 kilogram times acceleration due to gravity 9.80 meter per second squared and times 0.600 the amount of the height h. This will give us the amount of the potential energy at the beginning of the projectile motion, 4.12 joules with respect to the floor. So, combining the kinetic energy 0.350 joules and the potential energy 4.12 joules, we have the total mechanical energy of the system at the start of the projectile motion, 4.47 joules in three significant figures. So earlier, we already have computed the total mechanical energy of the system at the start of the motion, equal to 4.47 joules. How about when the system is about to hit the floor? What do you think is the total mechanical energy? So we start computing the final kinetic energy, case of F, which is just 1/2 of the product of their combined mass, 0.700 kilogram, and the square of their final speed, 3.58 meters per second. So in the case of kinetic energy, being a scalar quantity, okay, we can use directly the amount of the actual speed, right? There's no need to get the kinetic energy um, for each x and y components. So this final kinetic energy of the system as they hit the floor has is equal to 4.48 joules. And for their gravitational potential energy, as the system reaches the floor, all their initial gravitational potential energy has been converted into kinetic energy. So there is no more gravitational potential energy with respect to the floor. That's zero. And so therefore, this amount of the final kinetic energy, 4.48 joules, is already considered the total mechanical energy of the system as they hit the floor. And if we compare that with the initial mechanical or total mechanical energy at the start of the motion, their difference is very, very slight. Okay, it can be considered as not significant. And that brings us to our conclusion that in falling from the tabletop to the floor, the mechanical energy of the system remains constant or is conserved. So, on this note, may I say mabuhay. Till the next episode, MashaAllah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.